You might remember in a previous video how we equated the centripetal force with the gravitational force. You see, it was Newton's genius to realise that something like the moon is going in a circle for a reason. There's a force causing it. Of course, previous scientists thought the moon was made of this mysterious fifth element, the quintessence, and its natural motion was to go in circles. That was Aristotle. But Newton went, hang on, no, the moon's just ordinary matter and it's going to travel in a straight line unless it's required to do something different by a force. So why does the moon go in a circle? Because there has to be a centripetal force on it, just like anything else going in a circle, but that centripetal force is provided for by gravity. So the very same force that causes an apple to accelerate to the ground on Earth is the same force that causes the moon to accelerate towards the ground, but of course it's in a stable orbit. So if we can actually then equate these two and say that the centripetal force required is provided for by the universal gravitational force here, and we can think, well, how fast would we have to be going to be in a stable orbit? And that is the definition of an orbital velocity. Strictly speaking, it's a speed because it's not going in a straight line. So it's the orbital speed in which it's required to maintain a stable orbit. So let's just multiply both sides by r, which will get rid of one of those. This mass here is the mass of the satellite, okay, because that's the same, that's m1, and m2 is the mass of the planet. So that gives us v squared equals big G, I'm going to call it big M on r. So v is going to be equal to the square root of big G, big M on r. Now that equation there is not a green boxer in terms of it's not in your HSC formula sheet, but that bit of derivation is a bit of derivation you need to be able to do. So the orbital velocity is the speed required for a satellite to maintain a stable orbit. If it goes too slowly, it's going to spiral in and smash. If it goes too quickly, it's going to spiral out and escape forever. Actually, the moon is just a little bit too fast. It's slowly escaping the Earth by about a centimetre or so every year. So if we could slow it down, we'd end up being able to get it back again. Okay, so let's think a little bit about this thing in a stable orbit. If it's in a stable orbit, and we know what its speed it's going to be, well, speed is simply the distance divided by the time when it's going in a circle. So the distance it travels is 2 pi r, the circumference of the circle. So we can say the distance that it travels divided by the time, well, the time is the time for one period, one complete revolution, and that's going to be the speed, which we've just derived as big G, big M on r, well, the square root of that. So we can equate those two. Now this is interesting because many years before Newton came along, a guy by the name of Kepler, you might remember him from year 11, he was working in Uraniborg, that was Tycho Brahe's observatory long before telescopes, through lots of really careful observation, worked out that there is this mysterious relationship that connects all of the planets orbiting the Sun. That is, the cube of their radius divided by the square of their period is equal to some constant, some mysterious constant for our whole universe. And so that's kind of ticking away in the back of Newton's mind as he's doing this. And can you kind of see where it's going to go here? Can you start to sense that his pen is scratching a little faster over the parchment there? Well, let's square both sides to get rid of that square root sign. And now multiply both sides by r to get rid of this r down here. So that's going to make that r cubed up there. So we end up with 4 pi r cubed on t squared. This is feeling very, very Kepler-like to me. Big G, big M. Let's move the constants over the other side. We end up with r cubed on t squared equals big G, big M on 4 pi, whoops, I forgot my squareds up there, 4 pi squared. This is a constant. Big G is a constant. M is the mass of the Sun in this case, so it's a constant. And 4 pi squared is just a constant. In other words, Kepler's mysterious constant here comes out in Newton's work here. And so he was able to confirm as he works through what would be the orbital velocity, the stable velocity something would have to have in order to be in a stable orbit. Out of that pops Kepler's laws of motion.